is really Higgs phenomenology, and then what it means for the beyond the standard model physics. The outline of the 3 lectures are as follows. So in the first part, I'll talk about the Higgs in the standard model and then cover the experimental situation. And then in the second and the third lecture, I'll talk about the Higgs and the 4th generation, the minimal supersymmetric standard model. And then in the third lecture, it will be composite Higgs and then other bit more exotic Higgs phenomenology. Now, so let me start with this first part where I talk about the Higgs in the standard model and the experiment. So let me start with the motivation of why we're interested in the Higgs itself. Now, of course, this was big news of the last year, was that a new particle with a mass of 125 GeV was discovered. Now, if you don't know how big this is, whenever you're puzzled, you go to Google and then you Google yourself to death. Now, what you could do is you could look at Google Trends, which is, it shows you the prevalence of the searches for the Higgs on Google. You see that there are peaks, and obviously the July 4th peak is the discovery of the Higgs, but there are other peaks as well. Now, it's interesting to go and look at what these other peaks are. And you see that there's a discovery, but there is a small peak here where there's a Bristol Football Club chairman, Nick Higgs, was interviewed. So that's one of the instances where science beat sports. Now, what is our starting point? So, of course, there were experiments before LHC. So, the great legacy of lab, the electron-positron collider at CERN from the 90s, is that we know that we have electroweak interactions, which are the SU2 cross U1 gauge interactions. We know that we have spontaneous symmetry breaking. The masses of W and Z and the radiative corrections conform with this picture. Now, what LHC should answer is really how this spontaneous symmetry breaking occurs. Now, why we should, or why it was guaranteed that we should see something at LHC is that if you take standard model without a Higgs and look at the longitudinal W scattering, take the initial state of 2 W's with the longitudinal polarization, scatter into the final state, we have 2 W's with the longitudinal polarization. Now, if you only plug in the diagrams where you don't have a Higgs exchange, calculate, so this is just pictorially, there's other diagrams here. This type of scattering would have an amplitude which grows quadratically with the energy of the scattering. Now, that's a bad thing because you have unitarity bounds. If you do partial wave analysis, this matrix element needs to be, the scattering amplitude needs to be less than half. Now, it grows with the energy, so if you have an energy of roughly 1 TeV, you see that this theory would not be unitary. So therefore, you need extra degrees of freedom to come in before the TeV scale. So now we know it is a Higgs. The question is whether it's only the Higgs or something else as well. There are several basic options for the electroweak symmetry breaking and this unitarization. One is the weakly coupled model with the prime example of the standard model Higgs. There are other ways, like strongly coupled models, and this is what we will talk about in the lectures. It could also be a combination of the above, so a composite Higgs. So, are we seeing Higgs or not? So, we have discovered a new Higgs-like resonance at 125 GeV. The electroweak precision tests from lab confirm that tell us more about it. There's also the information that there's no new vector resonances from strong sectors seen at the LHC. So it does look like that these weakly coupled options are preferred. And again, this is one of the things that I would like to cover in the lectures, to quantify how precise this statement is right now. The next thing we'll also cover is the motivation for having extended sectors at the TV scale, so having beyond the standard model physics, and one of the brain motivation is the naturalness. So you have these quadratically divergent amplitudes, and something else probably has to cancel these contributions from, let's say, the top coupling to the Higgs. How you can do this? Well, one way is by measuring the Higgs cross-sections and the decay branching ratios, and this may be our best route to new physics. Of course, there's other observables, but at least we've discovered the Higgs, so we should have really measured this as precisely as possible. And as I will show, it does give us non-trivial information. So that's roughly what I will try to cover in these 3 lectures. So if you were not able to follow, I hope after the end of the 3 lectures, all these slides up till now will make sense. So let me start now from basics. So I start with the basics. I start with the standard model. So let's look at the Higgs in the standard model, where it is an SU3 color singlet, it's an SU2 doublet, and then it carries a weak hypercharge of 1/2. So in other words, it is a doublet. There's going to be a complex field, scalar field, has 2 components, and the Higgs boson sits in this lower component. Now it has a dual role. It will give electroweak symmetry breaking, and on top of it, it will generate the fermion masses. So let's first focus on the Higgs Lagrangian. So just look at the kinetic term and the potential. So the potential has two terms. There's the quadratic and the quartic. The gauge interactions, there's the gauge derivative, the covariant gauge derivatives. And in this covariant derivative, you get the coupling of the phi field, so the Higgs field, to the gauge bosons, the W's, and the hypercharge, the gauge boson of the connected with the hypercharge. So let's see how the electroweak symmetry breaking occurs in the standard model. So this potential has an instability, so that's the Mexican head potential. If you draw it projected into the 2 components, so phi, remember, is a complex doublet, so really it's 4 real fields. So just look at projection to 2 real fields. It will have a Mexican head-like form. You see that the minimum occurs away from 0, so the phi will obtain a vacuum expectation value. There, on top of it, there's the Higgs, the particle that gives us the particle. Now Higgs is the massive mode, so it has a mass. The mass is, in terms of these fundamental parameters, is 2 times mu squared, or since the value is mu over square root of lambda, lambda is the quartic coupling, it's 2 times the quartic times the v squared. Now if you plug in the numbers, it's actually interesting to look at how big these 2 fundamental parameters are. So the quartic is 0.1, 0.13. The mass parameter here is roughly 90 GeV, so that's the weak scale. We're talking about 100 GeV scale. And the lambda, the parameter is small, no? It's 0.1. If you want to compare to, let's say, the weak coupling, this is 0.6. The hypercharge coupling is 0.3, and this is an even smaller number. So one thing we learned is that the quartic is small. Okay? Now it also gives the masses to the W and the Z. This comes from the kinetic term, from the gauge, from this covariant derivative. You see that in the covariant derivative you'll have a coupling that couples the VEV to the W and the B. So in the end, if you expand it, you'll have the masses of the Z and the W, and the masses are given by the gauge couplings times V squared. For the Z is the gauge coupling of the SU2 plus the hypercharge gauge coupling. The W only has the SU2 gauge coupling squared. Now if you count the parameters, we start with the complex scalar doublet, so we have 4 degrees of freedom. unit scalar, that's the Higgs, that's 1 degree of freedom, and then 3 degrees of freedom went into the longitudinal components of the W and the Z. So to start with, the W and the Z were massless, so each of them only has 2 polarizations. Now they're massive, so they have 3 polarizations, the transverse and the longitudinal, and these longitudinal components are these 3 missing degrees of freedom that you get from the Higgs. Okay, now how do you get the fermion masses? So Higgs couples to the standard model fermions through Yukawa interaction. So the left-handed fields, fermion fields, are the doublets. The right-handed ones are singlets. There's the 3x3 Yukawa interactions, and then you couple to the Higgs. These are the leptons, the down quarks, and the up quarks. After electroweak symmetry breaking, these terms give you the masses. So I also kept the Higgs. You still need to diagonalize these 3x3 matrices, but what you see is the following. So that's an important thing to remember, is that the fermion couplings to the Higgs will be proportional to the masses. You see that it's because the Higgs always comes in the sum of the Web plus the Higgs. So the Web gives the mass, therefore the Higgs will couple with the same strength as the mass of the fermion. So that means that it couples most strongly to the top. Now the other thing that I wanted to go through is the custodial symmetry. So this Higgs sector in the standard model has an approximate global symmetry. So that's people call usually custodial symmetry. So it's an SU2 left plus SU2 right. It's a global symmetry. It's not exact. The part which is exact before spontaneous symmetry breaking is the gauge part, the SU2 left plus U1Y. And we'll see that how this global symmetry can be seen from the Lagrangian. Now this will be 2 pages of a bit more equations, but maybe it's still worthwhile going through them. So what you can do is I just rewrite this Higgs field as a bidoublet. So the only thing I did is I somehow did something stupid. So I had a very minimal description where I had just a complex doublet. Now I say, okay, I just write it as a bidoublet. So I'll take phi and do a little bit of algebra and include the epsilon phi star here. So I'm just doubling somehow the degrees of freedom. Why do you want to do that? Well, now it has a very nice symmetric form. The Higgs Lagrangian has a very symmetric form. In particular, if you look at the potential, the way you would get back to our previous form is you have a trace of these bidoublets now. Right? There's a trace here. Now, what it does make the symmetry much more transparent. So if you look at the gauge transformation, the SU2 left acts on the left on these bidoublets. The U1 hypercharge acts only as on the right with the sigma 3. And what you can see is that since it has a trace form, in reality, this part of this Lagrangian, the potential has a bigger symmetry. Even if you enlarge this into an SU2, this will still be invariant. So in the limit where G prime goes to 0, so the fact that I forget about the fact that this is really a gauge symmetry, the Lagrangian would have a global symmetry, the left times the right. So it really has an SU2 left cross SU2 right global symmetry. Now why this is interesting? It's interesting because it will tell you about what types of beyond the standard model physics are viable or will be viable phenomenologically. So this global symmetry is broken spontaneously once the Higgs obtains a web. So you have SU2 left plus SU2 right will be broken to the diagonal. Well, if you only act on the left on this matrix, you see that you will get a different matrix. If you act from the right, you will again get a different matrix, but if you act from the left and the right with the same transformation, since this is just the identity, the left times left dagger will cancel, shown here. Right? So you break this SU to left cross SU to right to the diagonal, where you have to have the left and the right transformation be the same. Now, why am I even talking about this? Well, it's because now you can understand the formula that I had before for the masses. So remember, the Z mass was G squared plus G prime squared V squared. But MW squared was very similar, except that there's a G prime squared missing there. And now we know that if I take G prime to 0, I have this global symmetry. Right? This global symmetry, in this global symmetry, the W prime, W minus, and Z form a triplet. Therefore, the masses should be the same up to the G prime corrections. Okay, so in case you didn't follow, let me just repeat once again. So there is this custodial symmetry. The bottom line is that even after electroweak symmetry breaking, there is an approximate global symmetry hidden there. Right? If you write it in a more textbook form, it's hard to see, so that's why I went into this maybe a bit more less elementary formalism. It's broken by G prime not being 0. It's broken by the Yukawa interaction. Now the important thing is that the radiative electroweak corrections agree well with the standard model. They have this approximate global symmetry built in because it's the standard model. Now if you come up with new physics extensions, they also need to have this custodial symmetry built in order to be viable. Okay. The last thing in this introduction is there's low energy Higgs theorems. What they say is the following. So let's say you want to know what is the matrix element for a certain process. I don't know, let's say the W scattering that I had before. But on top of this initial, the process that I start with, I emit also a Higgs. Now if you want to calculate this, there is a very nice relation, is that if you already know the matrix element for this guy, it's very easy to get the matrix element for the same matrix element but with an extra Higgs. So how you do that? Well, you use the fact that the Higgs really couples to the masses. So whenever you have a mass of a particle running in the loop, you just replace the mass plus this Higgs over the wave, because that's the coupling of the Higgs. The Higgs couples to the masses. Now, in order to get the coupling to the Higgs, you just Taylor expand this formula, the A of x plus h. Now, of course, there's the limit where everything has to be soft, or in other words, the masses have to be relatively large. So you only Taylor expand. Well, the Taylor expansion means that you take a derivative with respect to the mass of the fermions which are running in the loop. And it's really an illustration of the Higgs couples to the mass. And I'll use this formula further down the road to derive sort of the leading order expressions for the decay widths of in the BSM physics, the couplings to the Higgs. It's a very nice formalism. Okay, so now let me move on to the experimental situation. So it's almost 50 years since the hypothesis. So the Higgs mechanism and the Higgs boson were proposed in 1964. So that's 49 years afterwards. 48 years afterwards we had the discovery, and the big question is, why did it take so long? Now if you want to have more sort of life, it's really a lifetime of a human being, no? 50%, it's really long. You want to really understand. So let's look at the following. So you probably know this person. So you look at the Barack Obama, he's a president now. Now in 1964, Barack Obama looked like this. It was a boy. So it's really 50 years is a long So now let's look at the masses of the stuff we're made of, so the quark, the U quark, the D quark, and the electron. So in terms of this Higgs wave, the couplings are exceedingly small. No? You see that it's 10 to the minus 6, 10 to the minus 5 or so. So if you want to produce a Higgs starting from the protons, so the U and the D quarks, well, you have to do something else. Well, what can you do? You have to couple to heavy particles, like the top quark, where the coupling is order 1. Now you pay a price. The price to pay is the fact that you have to go through a loop. But you really understand why it took so long. It took so long because you have to pay either the price of coupling to the ordinary matter where you have small masses, or you pay a loop price and you have to produce gluons from somewhere. Now, LHC has PP collisions, so there's many gluons in the proton, and this really effectively overcomes the loop suppression in glue-glue goes to Higgs. So this will be the dominant production mechanism. You take a glue-glue, there's a top in the loop, you couple to the Higgs. Now also the Z and the W are massive. The couplings are still order 1, so 0.4, 0.3. So the other important production mechanism will be the associated production of the Higgs, where either the Z and the W, where you exchange the Z and the W in between. And then you also have a vector boson fusion, where you would have 2 jets plus a Higgs, and the Higgs is being produced from the W or the Z being exchanged with the initial partners. There are smaller cross-sections than the glue-glue to Higgs, but they're also phenologically important productions. Now the Higgs decay is the same story. Now it will decay through the heaviest particles possible. So the open channels will depend on the mass. There's the Higgs to the 2 fermions. The coupling, as I said, is proportional to the mass of the fermion. Or you can go through the loop, and as you know, the important channel is the diphoton channel, where you would have in the Higgs stress frame, you would have monoenergetic photons, so that's an interesting or experimentally useful signature. So if you look at the different branching ratios now as a function of the Higgs mass, first of all you understand that if the Higgs was heavier, the TT bar would only be possible, the Higgs to TT bar would only be possible once the mass of the Higgs is heavier than twice the top mass. So you see that the channels open up when the Higgs becomes massive enough, the same for the WW, where the threshold, we're just sitting sort of on the opening up on the threshold. The brown line here is the 125 GeV line. And the amazing thing to note is that there's many channels open. BB bar, the tau tau, charm charm, the diphoton, the glue glue, the Z gamma, and so on. So many channels are open. So 125 is a special number. Higgs at 125 GeV has many branching ratios which are order 1. So that's very nice. So there's many modes that are observable at LHC. I mentioned already Higgs to gamma gamma, Higgs to ZZ, Higgs to WW, Higgs to BB bar, Higgs to tau plus tau minus. It's dominated by Higgs to BB bar, roughly 60%, followed by the Higgs to WW, 20%. Then the glue glue will be hard to see, 9%, tau tau, and then so on to smaller branching ratios. And furthermore, you also have many production mechanisms that I mentioned already. Now, there's an unexpected benefit to this. So there's many branching ratios, there's many cross-sections. So let's say if I ask you the following, well, how can you tell whether you're seeing 1 or 2 resonances? So that's the energy, like if you're looking into the diphoton channel, it would be the mass of the invariant mass of the diphoton pair, and you would say, okay, the way I can see the 2 resonances is I plot the number of events as a function of this diphoton pair mass, and I will see these 2 bumps, and I will know that I have 2 resonances. Well, what will happen if these two resonances coincide. Well, okay, it looks like there's nothing you can do, no? Well, not so, because even if you have the resonances which overlap within experimental uncertainty, and by the way, the standard model decay width of the Higgs is 4 MeV, while the experimental resolution is 1 GeV, right? So even if you have the difference between these resonances is much bigger than the decay widths, but still at 1 GeV, experimentally it will look like one resonance. Okay? So you have these degenerate resonances. Can I tell whether I see one resonance or I see two or more resonances? And the answer is yes, I can tell, because there's many modes measured in different production and decay channels. Right? And the way to think about it is that I have, let's say I have many cross sections, I have many branching ratios, so it's really a vector of the branching ratios, a vector of the cross sections for each of the resonances. They get summed over. And since this is a direct this is the outer product of the cross section times the branching ratio, well, if I only have one resonance, this type of matrix would have rank 1. No? It's only one vector times one vector. It's a rank 1 matrix. If I have two resonances, it's a cross-section times the branching ratio for the first, the cross-section vector times the branching ratio vector for the second. So this would be rank 2. So we measure the rank of this matrix, you would know how many matrices, how many resonances you have up to the degeneracies. Right? Now, if you look at this, what you are able to measure, so there's different decay modes, ZZ, gamma, gamma, W, W, BB, tau, tau, and different production modes, you really have a matrix. There's many production times the decay channels that you can measure. The checks mean that there is some sensitivity there. You also you see what the significances are right now. You see that you could, in principle, do this. One other way, what I'm telling you is that we have an over-constrained system if I'm talking about one resonance. Right? So there is a lot of information in the fact that I have many branching ratios and many production modes. So from now on, I will just not care about this exotic case where I have more resonances, and I will assume there's one Higgs that we saw, and let's see where it leads us. Okay, so there's many production modes times the branching ratios. So this is where the information is really hidden. So if you want to do the fits, you want to use a table like this where you have a production with a particular production and a particular decay. Now what you usually see in the talks is something different. For instance, you could assume that the decay modes are the standard model ones, then you measure the cross sections. What's plotted on the x-axis is the cross section divided by the standard model cross section. So if you're sitting at 1, the cross section agrees with the standard model. The green line here is the average over all the modes, and the